Okay, now just first of all, I would like to emphasise in this video, we're going to be talking about setting up differential equations. And I'm going to go through 5 different examples, and I want to get through them as quickly as possible. But I want you to realise that some differential equations in exam 2 cannot be solved without a calculator. The ones that I'm going to go through today, most of them, well, we can solve without a calculator, and that's what I'm going to do. Now, of course, we know that we've used dsolve, don't we? We've used dsolve to solve a lot of these. If you ever have a differential equation, but the problem is, if you don't know how to set it up, there's no point using dsolve, is there? You need to set up the differential equation first. And what was dsolve? Dsolve was, what was the shortcut? Menu, then you press 4, then you press D. Okay, and that brings up good old dsolve. Now, I might sort of talk about dsolve and how you solve that with dsolve, and you definitely want to practice, but I'm going to do these by hand. Now, a lot of the time with differential equations, we're looking at populations, which can be increasing, decreasing. And we're also, the reason why in Year 11 Gen A, you did the topic of, I guess, wasn't it like constant of proportionality? Did you do that last year? Okay, is because then that relates to differential equations. Now, importantly, I don't know what happened there. Okay, so that's disappeared. First of all, this question's asking us to find the constant of proportionality, and a lot of the time you have to find that. But a bacteria culture starts with 1,500 bacteria. So what we're going to do is we're going to write, okay, at t equals 0, we've got 1,500 bacteria. Now, what the hell does that mean? We don't really know yet until we read the rest of the question. The population grows to 4,500 after 2 hours. So I'm going to say t is equal to 2 hours. Then we've got 4,500 bacteria. Now, what do you notice about the bacteria? Is it increasing or decreasing with time? It's increasing. So we've got a differential equation. But what we need to do, and what you guys need to realise, is that we need to declare what variables we've got. I'm going to let big P equal the population of bacteria. And what goes after that? At time t hours. So I've defined that. Okay. Now, therefore, we know that the rate at which the population is changing, dp dt, that is proportional to p. Now, if it's proportional to p, what else can I say? What does that mean? If it's proportional to, and it's in, wouldn't be there some constant? So therefore we can say that dp dt is equal to kp. Now, what type of differential equation have I got here? By the way, a lot of the time you have the good old type 3s. Because I've got dp dt, and what have I got here? P. It doesn't make sense. So what do I do? Do the old flipperoo. Okay? Now, that means that dt dp is equal to 1 over k, I'm going to put that out the front, times 1 over p if you like. Following me so far? Now, we've got to solve a differential equation, and we've done this to death. I therefore can say that t is equal to the antiderivative of 1 over k, 1 over p, dp, okay, and that is equal to 1 over k log to the base of p, absolute value of p. I will get to why we can omit that in a moment, plus c. However, what can you tell you about the population? Population is greater than 0. Therefore, we can say that we can drop that absolute value sign, can't we? So only when you make some acknowledgement of that fact can you just drop that sign. And a lot of the time exam questions use that fact. So be careful before you just go ahead and drop that absolute value sign. Now, what are our initial conditions? So we've got t is equal to that. What are our initial conditions? At t is equal to 0, p is equal to 1500, and what else have we got? T equals 2. What have we got? P is equal to 4,500. Now, just for argument's sake, I'm going to use the nice value of 0. Okay? T equals 0. So what we've got is 0 is equal to 1 over k log to the base of p log to the base e of 1500 plus c. Now, I've got equation 1, but I've got 2 unknowns, don't I? Correct? So that's equation 1. Now I've got equation 2. So in order to find this constant of proportionality, we have 2 simultaneous equations. The next one is t equals 2. We've got 1 over k log e to the 4500 plus c. All right. Now how do we go ahead and solve that by hand? What would we do now? Yeah, let's do equation 2, because c plus c, we're going to get rid of the c, aren't we? And we're going to do this by hand. Now, of course, you get a calculator, you do that, but I'm going to say 2 subtract 1. What is that going to give me? Well, 2 subtract 0 is 2, and that's going to give me 1 over k log e to the 4500 over 1500 is 3, log e to the 3. That's pretty awesome. So I've got, now what about if I get, I'm going to get k over here, so I might go 2k is equal to log e to the 3. Maybe I can say that k is equal to a half log e to the 3. We okay with that? Or we could say, how else could we do that? We could say that k is equal to, use the reverse power, and we could say that k is equal to log e to the root 3. Do you agree with that? Brilliant. Now we've found, what have we found? We've found the constant of proportionality. A lot of the time that's the hard part, I guess. We've solved a differential equation. Not quite. Have we found c? Thank you. So what's c? Let's sub in our value. I might say that k is equal to log e root 3. So we've got 0 is equal to, we'll sub it back into 1 if you like, 1 over log e to the root 3 log e to the 1500 plus c. What do I do from there? What do I do from there? Cry. Okay. What is it? Yeah. How do I'm going to pause this here just so we don't. So I've just resumed the video now because we have a value for c, and we also had our differential equation that we solved to have t in terms of c. To find c though, rather than go ahead and use this, by finding this log e to the root 3, that we couldn't have applied log laws there. Okay? So I left that value of k there. So I've got 1 over k log, the natural log of p over 1500, which now we can use if you wanted to, that is 1 over log e to the root 3, log of p on 1500, and that's our differential equation. Now, this is just a constant, but you can't simplify. I just wanted to make sure, because some students would actually do some crazy things and try to invent log laws that don't exist. Okay, because sometimes these differential equations, it's the algebra that can really screw us up. Okay, now, so that is, now the question was, and the population after 5 hours. So the question is now, at t equals 5, What is P? Well, we've got to solve that differential. We've got to solve that. So let's find that out. We've got 5 is equal to 1 on log to the base e of root 3. Log of P over 1500. Now, what I'm going to do is I'm going to get that, I'm going to say that that's 5 log to the base e of root 3 is equal to log to the base e of P on 1500. Now, you know what I might do though? On the left-hand side and the right-hand side, maybe if I do that power business, root 3 is 3 to the power of a half, isn't it? So couldn't I say that this is 3 to the... Jeez. 3 to the power of 5 on 2 is equal to log to the base e of P on 1500. So what can you tell me? What does P on 1500 equal? 3 to the power of 5 over 2. Now 3 to the power of 5 from memory is 243. 243, the square root of 243. So P is equal to 1500. Jesus, I'm busy, aren't I? 243. Okay. So this would make sense. What's the square root of 243 roughly?
9 root 3.
9 root 3. Yeah? So that's 9, isn't that 1350? 13500? Root 3? There you go, we've just done that by hand. Now, I don't know, if I was to go ahead and how could I just do that on my CAS? Now, I'd like you guys to do that on your CAS, please. With good old DSolve. Now, you wouldn't go ahead and waste all of this time when you have DSolve, would you? So I'm going to pause it. I'm going to get you to do DSolve. And remember, you've got to put in your initial conditions and see if that does. Now, in radioactive decay, the rate of decay is proportional to the amount of sample remaining. Now, once again, this is very straightforward and simple and very comparable to the one we've just done. If we have X milligrams of what? X milligrams of, is it radium? At time what? At time T what? Light years? Years. Okay, good. Now, I'm going to call X0 though. I'm going to call X0 the initial mass. Okay, now, first of all, what's our, now we've got a differential equation. What are we trying to find? dmdt. Beautiful. Now, dmdt, oh jeez. Oh jeez. All right, dmdt.
So then should it be milligrams radium?
You've labelled it X.
Oh, okay. Oh, yeah, sorry. Well, M milligrams radium. Yep.
I like that.
Okay. Now, dmdt is proportional to what? What's the initial mass?
Negative dmdt is proportional to m because it's saying the rate of decay, which is going to be negative.
Yep.
So it's proportional to the mass.
X milligrams.
Well, you can do it with positive K, but when you solve the K, you get negative.
Yeah, that's true.
So dmdt is but we're going to say it's proportional to
Because
m.
technically we can do either. Yeah.
Okay. And therefore, we're going to say that dmdt is equal to what? Km, isn't it?
Yep.
Now, such that K is what?
Yeah.
Less than 0. Beautiful. Now, at T is equal to 1600, what is our value for M?
200.
100.
And X0 equals 200. Or
and t equals 0, m is equal to 200. In other words, x0, if you like, is 200, or what we started with, or m0. Now, good. So what we've got to do is we've got to set up our differential equation. Now, if we've got dm dt equals km, well, guess what? It's a type 3 differential equation we need to solve. So we've got dt dm is equal to 1 over k times the 1 over m. Now, isn't that, it's exactly the same thing, isn't it? Okay, but what I wanted to emphasise is that a constant proportionality doesn't have to be positive. In this case, it's negative, and we would solve exactly the same way we solved before. Just, Ben, you had a question. Would you like the question to be on the video?
Oh, I don't mind. Because k is the constant, right?
Yeah.
Can we
Resume this, because this time we're going to go to the next one, and then this time, this is a really good example because good old Newton did a lot of things, including he work around this stuff, which is thermodynamics, which is Newton's thermal or Newton's law of cooling. Now let's have a look. We don't need to be told the formula for Newton's law of cooling. It's in your textbook as well, but and it's in exams. We're going to look at some questions relating to this stuff. The rate of cooling of an object is proportional to the difference in temperature between the object and its surroundings. So let T degrees, big T by the way, be the temperature at time t minutes. Now, here's the problem. Try put this in your calculator. dt, little t, all right? That's fine. Is proportional to what? What's it proportional to?
50 degrees minus 20 degrees.
No. Haven't I just stated this? It's proportional to... Let's have a look. This is known as let the room temperature be maintained at 20 degrees. And the object cools from 50 to 30. Big T minus 20. Thank you. So therefore, I've got dt, little t, is equal to kt minus 20. This is Newton's law of cooling. But of course, what do we have? We have this big T here and we have this little t there. So what type of differential equation is it? It's the old flipperoonie one. Flip-a-rooney. Okay? Flipperoonie. So, what we've got to do is we've got to do the old flipperoonie as well. And yes, Ben, 1 over k. 1 over t minus 20. And look, a lot of these do turn out to be, when we solve them, they become logarithms, don't they? Yeah. Just because of the, it doesn't mean they always have to be, but you might get some in your exam too, and they become really, really ugly. But it's a calculator thing, you don't have to do it by hand. So, therefore, what we can say is that t is equal to 1 over k, 1 over big T minus 20 d big T, which is equal to 1 over k log to the base e of absolute value t minus 20. Are we okay with that? Yep. Plus c. Now, what am I missing out on now? What do I have to say? Isn't big T minus 20, isn't that doesn't that have to be greater than something?
It has to be greater than 0.
Thank you. So therefore, doesn't T have to be greater than 20? So therefore, wouldn't you say that this is only for up to room temperature, so therefore wouldn't you have to say that T is greater than 0?
Is that T minus 20? Is that saying like it can't become colder than like...
That's right. It can't become cold in the room temperature. So, what we've got now is that is all of a sudden 1 over k log to the base e of t minus 20 as a bracket, but that's not an absolute value, plus c. Now, what do we do now? We go at t equals 0. Much the same as what we've been doing. Big T is equal to 50. And t equals 15. Big T was equal to 30, wasn't it? So they're our initial conditions. Now, of course, you couldn't go pump this into the calculator because we haven't found the constant of proportionality yet. So what do we do now? Let's go ahead and at t equals 0, big T is equal to this. You know, it might, I'm just going to put in this one, and we're going to go 0 is equal to 1 over k log e to the 30 plus c. And we've also got 15 is equal to 1 over k. 50 minus 20 is 30. Yep. Log e to the 10 plus c. And what do? We want to get rid of c, don't we?
Yeah.
So what we're going to have is, I'm going to just do equation 1, equation 2, and we're going to say that 2 subtract 1 is going to give me 15 is equal to 1 over k log e to the 10 minus 1 over k log e to the 30. We okay with that?
Yeah.
Now we can apply our log laws, which is 1 over k log e to the 1/3. Do we agree? And now we can say that k is equal to 1 over 15 log e to the 1/3. Can we do anything with that? You probably couldn't. What?
You negate 1 on 3 to make it negative 1 on 10 log e 3.
Yeah, you could do that. Yeah. Yep. So that's a good idea, Jordan. You could do that. Perfectly legal. Very good. So we found a constant of proportionality, have we not? We've set up a differential equation. What is the temperature of the object 10 minutes after it was 50 degrees? Well, didn't it start at...
Yeah, we don't know yet.
So at T equals what? 10. T equals 10. So we want to know at T equals 10. But we've only found K.
When it asks for set up a differential equation, what exactly does it want as the final answer?
It wants your differential equation as T equals 1 on or 1 on K.
What is the value of k?
It wants this, but we want to know what K is and we want to know what C is.
Okay, so that's your final.
That's the final answer. So we haven't set up the differential. We've set it up, but we haven't solved it yet. All right. So I'm going to get my little. Now let's do the same thing. How do we go ahead and find? We've found K now in terms of everything else. So therefore, what can we say about C? What's C equal to? Someone just tell me. C is equal to? Negative 1 over K log E to the 30? 30. Okay, so now let's write our differential equation. I've got my differential equation is 1 on K log E to the T minus 20 plus C, which is minus 1 over K log E to the 30. Oh my goodness. Oh my God. That is, now I can use my log laws, T minus 20 over 30, and we can sub in our value for K, but we're going to leave it like that. How are we feeling about differential equations now?
Fun.
They're fun, aren't they? But we haven't looked at the salt ones, which I started with inadvertently last week and might have confused a few of you. All right? I'm going to explain the salt one this time. Now I did say to you, and I still say to you, that when we're... Now, I just want to make sure this thing's still going, and I don't want it to go for too much longer, because otherwise people don't watch it anyway. So you might as well try to make it a little bit shorter. All right. As I have always said, I don't care if this tank is square or whatever, draw yourself a nice cylinder, because then you'll feel really great. Do this, but be careful. A tank contains 2,000 litres of brine. Don't worry about the brine part yet. And it contains 2,000 with a concentration. That is not what's going in. That's how much salt is to start with in the concentration of salt. Pure water is run into the tank. Now, pure water is 20 litres per minute. I don't want you to worry about anything yet. Just write 20 litres per minute. And what we want to do is we want to first of all just define what we're actually looking at. We're looking at m kilograms of salt at time what? T? T micrometers? Micro years? What is it? Minutes. Okay. Now, what do we want to find? Don't we want to find dm dt? We want to find the rate of change of salt. Good. So what we want to say is dm dt is equal to simple rate in minus rate out. Now we did go through that. But let's have a look at usually the rate in. Now I've got 20 litres per minute going in. However, it does say that pure water. Now I've got it. Now what is my rate? M's in kilograms. Okay? Kilograms. And T's in minutes, isn't it? So if I've over here got a minute and I've got, what's missing? I need what? I need, the litres need to cancel out. And this is kilograms. But what it is because these are going to cancel out, kilograms per minute. It's just a unit thing. Ah, they're the same unit. Kilograms minute. But yes, it is pure water being run in there. So it's 0 kilograms per minute. So the rate in is equal to, I'm just going to get my other little pen here. The rate in is actually equal to 20 times 0, which is 0. Thank you. Minus the rate out. Now let's have a look at the rate out. Once again, the rate out, what's coming out? We want kilograms per minute, don't we? Now, let's have a look, and let's not be careful though. Pure water is run into the tank at 20. The mixture is stirred continuously, yada, yada, yada. Who gives a hoot, right? But a tank contains 2,000 litres of brine with a concentration of 0.2 kilograms of salt per litre. Set up a differential equation for the amount of salt in the tank. So how many kilograms of salt is in there? No, we've got 0.2 kilograms of salt per litre is the concentration. Aha. So don't we want a kilograms and we want a minute?
Yeah, it's flowing out at a rate at 20 kilograms per minute.
It is
20 litres per minute, sorry. And there's a concentration of X over 2,000 litres.
So it's 20 litres per minute going out, yes?
Yeah.
Good. And it's 20 litres going out, and we've also got, we need to have, what is it, kilograms per minute. So how many kilograms of salt are at time t?
X over 2,000.
Is it x or we've used
Yeah.
m kilograms of salt? M kilograms of salt, good. Over. Now think about it. What's the volume? The volume is always 2,000. Is that it? Now that 2,000 is then times by 20.
Yeah, but isn't it just 22,000 at this point because the same amount of liquid volume?
Yes. Oh, we're going to go through another example. So be careful then. So what we've got is 20 litres per minute. I'm going to just do this times m kilograms over 2,000 what? Litres. They're going to cancel out. Yes, we've got the same unit that we've got over here. So therefore we've got minus 20 m over 2,000. So our differential equation that we need to solve is 0 minus, that's going to cancel out, m over 100 what? Kilograms per minute. That's our differential equation. We're done. Now that's an easier one, okay? Because inflow and outflow litres per minute are the same. So I'm going to do one last one before we go. We don't now, it just says here, look, we've set up the differential equation. How much salt will remain after half an hour? So, okay, let's do that. We've got dm dt is equal to, now this is what I wanted to show you, is equal to minus m over 100. What do we do to that differential equation? Thank you, we do the old flipperoonie. Which means that we've got 100, negative 100 over m. Is that right? Now, therefore we can say that t is equal to negative 100, 1 over m dm, which is equal to negative 100 log to the base e of m plus c. Can you tell me though, how, now this is the thing, it doesn't directly tell you though, but it can, this is brine. Brine means it's like a salt solution. So, oh look, we've got all this little salt in here. And all of that salt has, well, if I've got 2,000 litres times, what, 0.2 kilograms of salt per litre, isn't that going to be equal to 400 kilograms of salt? Because that's our initial condition. Okay, so what we're going to say at t equals 0, m is equal to 400. There's our initial condition. So we now can then go ahead and solve for that. So I've got 0 is equal to negative 100 log e to the 400 plus c. I can therefore say that c is equal to 100 log e to the 400. And I can then go t is equal to minus 100 log e to the m plus 100 log e to the 400, which is equal to 100 log e to the 400 over m. And that's our differential equation. We now have our differential equation. Keita, you're looking at me, no, it's all good. Okay, so now, and then of course, you know how much salt will remain after half an hour? Yeah, easy. You know, t equals 0.30. Solve at what time the concentration be that, and that's just solving. Now, at what time will the concentration be 0.1 kilograms? Let's try and do this just to show you the algebra. Okay, 0.1 kilograms. So if I had, so I've got 100 log e to the 400 over 0.1 is t. It's asking you for what time. So that's 100 log e to the 4,000. Can you really do much with that apart from work that out in a calculator? No? That's right. So that's fine. And of course the other one is the other way around. That's probably the harder one. How much salt will remain after half an hour? So 30, this time, but a lot of you don't, I'm surprised how many kids don't know their log laws. 30 is equal to 100 log e to the 400 over m. How do I go ahead and solve for that? Okay, good. So I've got, let's say 1 over what? 3 over 10, good, is equal to log to the base e of 400 over m. Because t equals 30 minutes. Okay? Now, what's the inverse of a log? Good. So this is what we're doing. A lot of students don't even realise this. They've got to take the exponential. I'm taking the exponential of that side, and I'm taking the exponential of that side. And like, I was surprised how many kids don't realise that by doing that, this e to the log e actually cancels out. And I'm left with e to the power of 3 over 10 is equal to 400 over m. which therefore implies that m is equal to 400 over e to the 3 to the over 10, whatever that is. Yep.
What the top one?
Yeah. I'm going to resume for the last one. This is the ones that you are going to have to think about it, but once again, we draw our tank and it's the same tank. The same tank which has 2,000 litres in it. 2,000 litres. This time the brine with a concentration of 0.1 kilograms per litre, which means that 0.1 kilograms, there's 2 at T equals 0. There is how many kilograms? M is equal to 200, isn't it? Is that right? Now, M is equal to 200 kilograms. So we're doing the same thing, but this time it says it's run into the tank instead of pure water. So we've got 0.1 kilograms of salt per litre. So once again though, let's not get too complicated. Kilograms per litre multiplied by, we want dm dt, which is equal to rate in minus rate out, which we know is in kilograms per minute. So I want a kilograms per minute in the top. So let's make that minute, and that.
Just a question on the starting salt.
Just one sec. Let me just finish this, okay? Well, I'll get to you in a second. All right. So kilograms per litre coming in is equal to 0.1 and then litres per minute at a rate of 20 litres per minute. So the rate in is pretty easy. But the rate out, let's have a, and the mixture runs out at 18 litres per minute. 18 litres per minute, and we also need to know what else do we have to find? This is the tricky part. Now, remember that we want to have kilograms per what? Litre. Now, we've defined M as the amount of salt in kilograms. How many kilograms of salt are there at time t? M. So, it's subtract what goes on top? M. Now, what goes on the bottom? Well, kilograms per litre. The volume starts at what? 2,000. And every time I've got 20 litres coming in and I've got 18 litres coming out, thank you, plus, yeah it is plus 2t. Done. Now, what I suggested last time is actually, in fact, this is related rates. But I think that if I simplify it a bit more and look at the units, it makes it easier. So, one sec, Ben. Shh. So that is equal to 2 minus m over 2,000 plus 2t. And of course, be careful. Oh, times what? Thank you. Times 18. Now, of course, when possible, you would then look for something to simplify because you might have to do this in your calculator. I'm going to divide the top by 2, so I've got 9m, 1,000 plus t. Now, we've just set up a differential equation, and then of course we go ahead and solve that as we've done normally. Okay? Now, I'm going to stop there and now you can ask your questions. I know that that's a lot, but I've started at the easier ones, which tend to be population. It could be a population of wombats increasing or decreasing, Newton's law of cooling, and then you've got tank questions where the inflow and the outflow are the same, or the rate in and rate out. They're a bit easier than this last example. I'm going to stop there.